Yeah, I think it's on. So my voice is still coming back, so if you can't hear me, you may just need to move up a little bit towards the front, but hopefully I can keep up the volume for the talk. But I'm going to be talking a little bit about predictive modeling of pulsar scintillation, and in particular, one model that I've been working with. So first of all, why are we interested in modeling pulsar scintillation with something that can make prediction? So as you've already heard, especially in the first talks, we see that there's persistent structure in the secondary spectrum, and some of the early work done by Alex Hill and Dan Steinberg and others shows that we see substructure in the secondary spectrum that actually lasts for the whole time that it takes to transverse kind of through, or that the pulsar takes to transverse across that structure. And so that means that at least some of the scintillation that we're seeing isn't completely random, and we have the potential of actually predicting it and modeling it. And we've also, there are kind of two sides to scintillation. And I think here we've talked more about using scintillation to understand pulsars, but there is another side, which is using scintillation to understand the interstellar medium. And predictive modeling can help inform both of these approaches. So with predictions, we can actually make tests based on our understanding of the interstellar medium, and then test those in order to see where our understanding might fall short. But we can also, if we can predict scintillation, then we have a tool that may allow us to remove scintillation from our observations. And so we can improve things like pulsar timing by better understanding scintillation. And we can also use an understanding of scintillation to inform scintillometry, or this use of using the scattered images as an interferometer to learn more about the pulsar emission itself. So as a quick review here, we've already seen this a lot now that it's on the third day and not the first day. But this is this picture that we're working in where we see these beautiful parabolic arcs in the secondary spectrum. And in particular, we see also these inverted arclets in the secondary spectrum. And so this can be explained with this thin screen model where we assume that the scattering is one-dimensional. And so then if you consider the scattering of this line of sight image of the source, the interference of this line of sight image of the source with these other scattered images, that leads to power along this main parabola. Whereas if you consider one of these scattered images interfering with other images of the pulsar, we get these inverted arclets. So when we have this case where we have distinguishable scattered images, we can get something like this from this model. But we're going to take it a step further and try to explain why we get this one-dimensional scattering that we see. And to do this, I'm going to work under this picture that was proposed by Whaley Penn and Yuri Levin in 2014, that we're actually seeing the result of grazing refraction of the pulsar light off of corrugated sheets in the interstellar medium. And so in this picture, you have many of these sheets that are distributed throughout the ISM. And it's only when you get this very high alignment of this angle of the sheet with the line of sight image to the pulsar, so that this angle here is very small. Then when you're in that limit, you can see that wherever you have one of these crests, you have a very large change in the column density through your lens. And so at these crests on the sheet, you actually can produce very high bending angles. And with this, you can, because of the curvature of the sheet, you relieve the requirement that you have these high differences in electron density between the sheet and the ambient interstellar medium. And so you can get this with just a very small overdensity or underdensity, and now we can consider both cases. And so in this case, that kind of explains why this picture might be nice, but what really is spectacular is that it gives you this one-dimensional scattering that we see in the secondary spectrum. And so this is a selection effect. It's because when you have this very low angle of incidence between a bright source like this star and a scattering sheet, like in this case we're seeing reflection off of a lake, then the perturbations along this sheet that are required in order to bend the light into your line of sight only have to be very small in this direction. But if it was trying to bend light, say, from here into your line of sight, you would have to have a very large perturbation. And so it's just this selection effect that leads to power distributed along a one-dimensional line. And this is what this model kind of relies on in order to explain this one-dimensional picture. So I'll give you a brief setup of the way that I've modeled this. And in here, we're trying to produce a quantitative model that allows us to make predictions. So to do that, we've used an approximation of a wave crest here as a parabola. And then we're using simple geometric optics here. So theta is the angular location of our image that we see being produced by, or I should say here that we're looking at a single crest. So we'll be comparing a single lensed or scattered image to the line of sight image to the pulsar here. So theta is the location of that scattered image. Beta is the location of the pulsar itself relative to the crest. S is this parameter that you've all seen before now that contains the distances within our system. And alpha hat then is the parameter that contains all of the physical information of our lens. So it contains the curvature of our lens as well as the column density through this sheet. And so if we know alpha hat, then we can actually predict for all times or for all positions of the pulsar where the scattered image will occur. And once we know that, because we're in this 1D limit, we can then just calculate the magnification by taking the derivative of the observed position relative to the true position of the pulsar. And what's nice about this model is that when you have a very large separation between the source or the pulsar and the crest, so when you're in these large delay limit here, then this alpha hat parameter depends only on this single parameter. So now we can describe all of the physics of our lens with a single parameter. And if we want to parameterize our lens and then use that to make predictions, we just need to determine this parameter. So how would we go about doing that? It turns out that in this, we also see a very simple relationship between the ratio of the magnification of our scattered image and the brightness of our line of sight image to the pulsar. So really just the magnification of the scattered image with the angular separation between those two images. And it depends now only on this angular reference separation, which again depends on this single parameter. So if we can measure the angular separation between the pulsar itself and this scattered image, and we can also measure the magnification of our scattered image, then we have all of the information that we need in order to figure out what this parameter would be if it is one of the crests from these sheets, and then we can make predictions from there. So how can we go about doing that? So as I said, we need angular separations between the images as well as the fluxes of the images. And we want to get these from the secondary spectrum. And now I think you've already seen this a few times before, but we have, in the secondary spectrum, we know that the location of this apex, of the apexes of these inverted or reverse arclets, tells us about where they are, where the actual image is on the sky, because of this, the way that the angular separation comes in to both the delay and the Doppler frequency. But we also need to know things about our scattering system, including this effective distance and the effective velocity. But luckily, as was shown in this 2010 work by Walter Briskin and many others, some of whom are in this room, with VLBI, we can actually determine the angular location of the images from the two-dimensional Fourier transform of the visibility. And something that I think hasn't been mentioned before in this workshop, but is actually quite striking about this plot, is that this this technique to get at the locations of the images from the phases, those locations are given by these cyan points here. So you can see that the error bars are quite big. But once you have those locations, now you can use delta theta as well as tau and FD to fit the effective distance and the effective velocity. And then you can use what they call back mapping to use the location of the apexes now in the secondary spectrum to get the locations of the images. And that's these red points here, which are much more precise. And so with this, you can actually get very precise measurements of the locations of the images in the secondary spectrum, or this delta theta that we want to learn about in order to constrain our model. So that gives us these angular separations between the images, but we also want to get the fluxes of the images, and this is not as straightforward. So we know that the flux of the arclets encodes the relative magnifications of the images. And so a summer student who worked with us here at Toronto, Beatrice Desi, tried to run a mask, this parabolic mask, through the secondary spectrum in order to measure both the locations of the apexes as well as the fluxes that are contained in an arclet at each location. And so here's some of the results from that. So here she's plotting flux versus the Doppler shift for a very small part here of the secondary spectrum. And you can see here she's marked with dots the arclets that you can also see by eye in the secondary spectrum, although possibly not on this projector. But it actually picks out the structure quite well. And it also allows us to compare the relative magnifications of these images in the secondary spectrum. But these are the relative magnifications of the scattered images. And what we actually want are the magnifications relative to the line of sight. But this is difficult because you have all of this flux at the origin, some of which is due to noise, and some of which is the total sum of all of the power. And so you have this difficulty in actually comparing to the flux at the origin. So what we've been working on is comparing to an arclet, or the main arc itself, in order to get that comparison. But we're still working on getting the precision of that measurement down to what we really need in order to test these models. But we can get the fluxes from the relative fluxes of the arclets. And then we can go ahead and test this. So at the moment, these are just some values that are pulled from the Briskin et al. Data, but not for a particular image. These are typical values for what they see from the arclets in the secondary spectrum. But if you have a lensed image with a magnification of about 1% and an angular separation of about 10 milliarcseconds, you can then fit this parameter for the lens and then calculate how the angular separation of this image and the line of sight image will change with wavelength. And we fit a power law to this over the same bandwidth that was used in the Briskin et al. Paper. And we find small power law exponents, but we do find this behavior where if the sheet is underdense compared to the interstellar medium, then as you go to longer wavelengths, the images move apart. So you get a positive power law exponent. Whereas if it's overdense, you see different behavior. You see the images move together at longer wavelengths. We can also compare this to what has actually been measured in that original 2010 paper. So here they've reduced the errors by actually combining many images so many arclets that they associate with each other, so that seem to be from the same part of the parabola. And they find for one arm of the parabola that they get a positive power law exponent. For the other arm, they don't measure anything that is positive or negative within errors. But they do get this small change in angular separation with wavelength. But we want to do this with a full analysis where we start with one of these images, determine the parameters that describes the lens, and then make this prediction. And so this is what Beatrice Desi was working on over the summer. And you can see here that even though our measurements of the angular separations are fairly precise, because of that error measuring the actual flux of the pulsar in the secondary spectrum, we get very large uncertainties on the angular separation. And so this is something that we're really trying to improve right now. Okay, so as we move forward, we want to work on getting higher precision measurements of those from the secondary spectrum. But we also want to be able to apply this to other systems where we might not have such a clearly separable images in the secondary spectrum. And we can use other techniques, including this deconvolution technique that Martin talked about, to try to clean up the secondary spectrum in order to get a better measurement for those systems. But what we really want are to make predictions, and to do that we want large changes that we can then test. And so we want large bandwidth observations, and we also want multi-epoch observations, so we can test how the magnifications and the locations of these images change over time. And so I have a quick preview of a couple of those observations in this vein. So this is data on pulsar B0834 plus 06 that was taken last fall, actually at the same time as last year's meeting. And this is a subset of the data. So you can see a few interesting things here. One is that we see both arclets, and we see this kind of diffuse filled-in parabola at the same time. And we only see one clump of arclets that appears and then moves through the dynamic, or moves through the secondary spectrum over time as the pulsar moves behind the lens. Yeah. So this is, we're still working on cleaning up this data. You can see that there's a lot of artifacts from RFI, as well as just from our bandpass that we're working on taking out. But it's kind of a preview of that. And the other thing we want, like I said, are large bandwidth observations. So this is B1133 plus 16. This is actually data that Ariel is now working on. And this just shows, it was taken at Algonquin, so that's why it's fairly low signal to noise. But you can see clearly how it changes with frequency. So you see not only what you expect, you get higher delays at low frequencies, but you also see that this kind of change in the power with frequency as well. And so we're really excited about using the GMRT as well with their new wideband receivers to do this same type of analysis with much higher signal to noise. And that's all I wanted to say.
So are those data from this case taken at the same time?
This is actually a single observation. So what I've done here is we have a 400 megahertz band, and I've just split it into 100 megahertz. I know there's been talk about this Fourier transform method to take out the curvature of the arc with wavelength. So I've done that here. So that's why it doesn't look like the curvature of the arc changes over wavelength. I've just removed that so that you can compare it more easily by eye. But yeah.
Checking if there's someone else who has questions. Yes, JP.
I was just going to ask, can you show the 0834 observations again so I can marvel in this window?
What sort of cadence do you have? What kind of
you,
spacing between observations?
Yeah, so it's not regular. You can see the MJD at the top. Some of them are separated by a day. Our largest, I think, is 3 weeks. And we do have some before this where we don't see the arclets. And then they appear after our second observation, I think, and then move through the spectrum.
We have the baseband observations for these.
Yeah. So this is actually Arecibo data. We also have the baseband, and we have the correlated data where you can clearly see the phase.
Mentioned that this was part of a VLBI series.
Yes.
To actually see where they move on the sky.
The reason I ask is because, of course, you're only going up to 80 microseconds.
Yes. And you can see that the power is extending. So that's the next thing to do with this is so this is actually puppy data, so it's quite easy for me to just run it through DSPSR and up-channelize it further. Yep.
What is the radio frequency here?
This is 327.
So the idea, you just mentioned, Daniel, was to repeat the 0834 observations of Riskin et al.
Yeah.
But have multi-epoch V of VI.
Yes. So we can actually look at evolution with time. And we also have higher, so we have a 50 megahertz bandwidth here with Arecibo, so we also have a bit larger bandwidth to work with.
Well, this is all just spectacular work, and what we're looking at there is one of the most gorgeous things I've seen in a long time. That really is brilliant. Let me just ask quickly on that. Have you projected the apex positions down onto the fringe frequency axis and seen what the motion across the sky is?
We haven't, no, I haven't looked at what their motion is over time yet. I'm still working on trying to get signal to noise.
That is really beautiful.
And seeing, yeah.
I had a question going back to your magnification, attempting to pull out the magnification from the arclets. And a couple of questions connected with that. So while it's true that the reversed arclets encode that flux information, isn't it also true that the forward arc itself has that same
Yeah.
flux information? And so did you consider working directly from the forward arc?
Yeah, so actually what we tried first was to deconvolve the arclets onto the main spectrum. But then we find that we have a lot of this kind of diffuse power that makes it harder to pick out which are actual images. So that's why we ended up using this. It's just easier to pick out these individual distinct images for our first test.
I'm going to ask Dana to show the deconvolution later, though.
Yeah. I just
in
have
itself very interesting, I think.
a quick follow-up on that. I mean, one of the things when you model this stuff, just in terms of theoretical mapping from the sky into the secondary spectrum, there's a Jacobian that comes into play basically because it's a nonlinear mapping from the sky into the secondary spectrum, and I wonder, is that something that you're taking into consideration as you try to extract these magnifications?
You mean in terms of the fact that it could be elongated in a second direction?
Well, maybe we should just talk about
Yeah.
this privately, but I'll just mention. So, for example, if you take more or less a
Equal diff would become smaller if it's further away.
yeah,
So I think that's what you're also
I
saying.
think I can describe it.
Yeah.
It could be useful to other people. I mean, if you take like a circular scattering disk on the sky and then see how that maps into the secondary spectrum. Yes, there's a nice clear parabolic boundary, but there's basically a ski bowl that fills in toward the center, and the slope of that ski bowl just has to do with this nonlinear mapping. I mean, if you take a uniform disk, for example,
Yeah.
and do that, so it's just
So,
a detail to worry about.
Yeah, at the moment we're just assuming everything is 1D, so we're not taking that into account, I think. But
So for example, since the delay axis is proportional to an angle squared, but you're saying even if I had a constant spacing and angle, then I have a non-constant spacing and delay, and since, if I now take an average of delay, I kind of change even though for factors that are totally constant, and in that particular example.
Yeah.
Now, in this case though, if you have discrete images that are inverted arclets, and then by the conclusion theorem, the relative fluxes, if they become individual images, don't have that problem.
Okay.
But it is true that you have to average, make sure that you get your whole arclet.
yeah, and that's something that we're Yeah. Yeah. But what what we're not doing though is accounting for the fact that this image may be displaced in this direction, right? Which we know is true when you look at the work that Briskin et al. Did, where they actually see that there's some displacement in that direction as well. So in that case, there's still work to do to try to make sure that you're getting all of the power. Yeah.
I think I should send you a copy of the graduate student I had working on this. He wrote a thesis on this data, which is not published, but I could send you a copy of the thesis.
Yeah.
It's quite a large file.
Well, I would love to look at it. Yeah.
That's J.J. Gao.
Okay.
Who's not in astronomy anymore, but he did a lot of good work. Most of the analysis in that paper came out of his work.
Oh, really? I didn't know that. Cool.